Hello! Today I'm going to explain switching regulators. Up till now we have built a linear power supply starting with the transformer and explaining every part of the circuit all the way up to a precision regulator. But you'll notice that most power supplies today use a switching regulator, and I'm going to explain how they work and why they are so popular. So let's take another look at our linear regulator and see what the difference is. So we are coming off of our transformer and our rectifier and filter. So we have filtered DC out here, and this is going to come to our pass transistor. I'll make this fairly simple, and our load is going to be here, and I'll just take that on back, and this is going to go to, I'll just make the simplest of regulators here, just a simple Zener diode for a voltage reference. And let's make that a 12.7 volt Zener diode, which means we should get 12 volts on the output. And we're starting off with a filtered DC, so it came from the mains. In America, that would usually be 120 volts or so. Step down to a 12 volt transformer, which after rectification and filtering gives us about 18 volts. So I'll just put 18 volts over here. So we have 18 volts over there, 12 volts there, and let's just assume that at this point we have 1 amp going through the load. I'm not going to worry about the value of this resistor. We usually don't. It just simply represents whatever circuit is out there. So essentially it's a variable resistor where the load can change depending on what the circuit's doing. So what do we have here? We have 18 volts on that side, on the collector of the pass transistor, and 12 volts on the emitter side. So we have a total of 6 volts from the collector to the emitter. And how much current? Approximately 1 amp of current. So how much power is that transistor dissipating? Well, that's pretty easy. Power is simply equal to the voltage times the current. So 6 volts times 1 amp means we are dissipating a power of 6 watts. That's a pretty hefty amount of power to be dissipating. Trust me, you could burn your finger on a transistor dissipating just 6 watts of power. I have. So we're going to have a huge heat sink on this to get rid of the heat, and a fairly hefty power transistor to handle the amount of power, 6 watts, that's being dissipated from that transistor. So what could we do to mitigate that? Well, why don't we get rid of some of this clutter to begin with and replace this with a switch. I'm going to erase the voltage reference because we're going to have a slightly more sophisticated circuit here. So I'll just put this as a little box with an R on it. This is our regulator circuit. Well, I'll put the diode back there because we will have to have some voltage reference somewhere, but it could be built into the circuit. So a voltage reference going there, and that's going to control a switch. Of course, it's going to be a transistor, but I'm going to just show it as a mechanical switch. And let's have that switch open at this time. So we have 18 volts over here, and this eventually goes down to ground, and so with no current going through there, we're not going to get a backup of voltage, so there won't be any voltage here. So 0 volts there, no change. 0 volts here. To get a voltage across here, we have to have current flowing through it. There is none. So at this point, we have 0 volts on the output. So we start with 18. 0 volts. How much current is flowing? 0 amps. So we have 18 volts, and we multiply that by 0 amps, and that gives us how many watts? We have no watts, except we also have no volts and no current. We have no nothing. So that's not very useful. So let's go ahead and close that switch and see what happens. All right, now the switch is closed. We have 18 volts here and no voltage division here. So there's our current flowing in there. Nothing between here and there to cause any kind of a voltage drop. So we are going to get a full 18 volts on the output, and whatever current we're going to get with 18 volts across this load, which is probably too much, maybe, maybe not, but it's not what we want. We want 12 volts out there. So we've got 18 volts, but what's our power dissipation? Well, we have, let's say, at this point, we still have 1 amp. I'm going to say 1 amp just to keep the math simple. Of course, with the higher voltage, we're going to get a higher current, but we just want to get an estimation here. So 1 amp, and how much voltage is across here? Well, what is voltage? It's a differential. What's your voltmeter measure? The difference between your red lead and your black lead. So 18 volts here, 18 volts there. What's the difference? 0 volts. So I have plenty of current, too much voltage, probably too much current, but I have 0 volts times that current. How much power do I have? 0 times anything is still 0. My power equals nothing. So I've got an undesirable situation here, too much current, too much voltage, but still no power. So the point is that if we had a switch there instead of a transistor, we could either have the switch open and have 0 watts of power, or have the switch closed and have 0 watts of power. But the problem is, now we've either got no voltage or too much voltage here. What could we do about that? Could we find a happy medium somewhere? Well, what if we turn this on and off at some regular interval? So let's turn it on and off. Let's just say 1,000 times a second. So it's going to go off, and so there's 0 volts on the output. And then we're going to close it and turn it on. And now we go all the way up to 18 volts. But then we'll open it again and go back to 0 volts. And we just do that over and over again, 18 to 0 volts. That's not going to be very desirable either, but no power, no power, no power, no power, no power. Could we somehow convert this pulsating square wave into a steady DC wave here? And you might think, well, why don't we use a rectifier? Well, we don't need a rectifier because it's already rectified. It's DC. It's already pulsing DC. All we need is a filter. Remember over here we had our AC. It goes through the transformer, steps it down. Then we go through a rectifier, which turns it into pulsating DC. Then we send that through a filter to smooth that out. And you can watch the previous videos to see how that works. So all we need to do is put a filter over here. So we could possibly do nothing more than just put a capacitor over here and put that in parallel with our load, and that would tend to smooth this out. So our output on the output side, instead of being on, off, on, off, on, off, it's probably going to go something like charge, charge, discharge, charge, discharge, charge, discharge, and go from maybe, let's just assume that this is going to go from about plus 10 volts to plus 14 volts. So it's going 2 volts high, 2 volts low, 2 volts high, 2 volts low. That might do it. We have an average of 12 volts with just a little bit of noise on it, and put a bigger capacitor on there, and maybe we can smooth this out even a little more. But could we improve that? Yeah, why not? Let's change that, and not just a capacitor, but let's put a couple of capacitors, maybe not so big capacitors now. That's probably going to take a pretty hefty capacitor, but now let's put a nice toroidal inductor over here, and for good measure another capacitor, and then the load. I'll put my variable line through there, my arrow, and so just to show that's going to most likely be a ferrite core, so I'll just draw that as it is. So now what does an inductor do? Well, it acts like a flywheel. When we try to push current into an inductor, it builds a magnetic field, or whatever magnetic field is there increases, and that increasing magnetic field generates a current in the coil, which produces what's called back EMF. It causes a current to try to flow in the other direction, creating a voltage across here that opposes the current coming in. So the current tries to increase, the inductor pushes back. If the current tries to decrease, well, now that magnetic field tends to collapse and causes a current that wants to go in the same direction. So if this current tries to increase, the inductor tries to keep it from increasing, and if this current tries to decrease, the inductor tries to keep it from decreasing, and so that's going to smooth it out quite a bit. So what we end up with on the output after going through that inductor is a nice, I'll just draw a little bit of ripple in there, a nice continuous DC. So we have a square wave over here, and the voltage is, well, what's coming out, we're just looking at an average of 12 volts. But it's going up to 18.0, 18.0, 18.0. But once it gets through this low-pass filter here, it's a pi filter, it's shaped like the Greek letter pi, it is smoothed out to a much smoother, almost nice smooth DC. Now, there is still a problem here. What if this resistance of our load, let's say it's some kind of a radio transceiver where when it's in the listen mode or the receive mode, it's not using much current, but you press the microphone key, it turns into a transmitter and starts using a lot of current to produce power to create radio waves. So essentially that's going to suddenly drop, and the impedance of the load is going to drop, so it's going to demand more current, and naturally coming through here we're going to have a drop in voltage. What do we do about that? Well, we have this smart switch controller here that sees that, and what it's going to do, let me kind of clean up my drawing here. We start out with a square wave, and right here I'm drawing a 50% duty cycle, meaning it's on 50% of the time and off 50% of the time. And if this drops, what it's going to do is leave it on longer. So each pulse, it's going to increase the pulse width. So now it has a longer duty cycle, let's say 75%, whatever. And so since the switch is on and we have the 18 volts here for a longer period of time than it's off, that's going to bring our voltage back up. And so now that's back up, and the operator lets go of the key and the demand suddenly drops. This goes to a higher impedance, needs less current. So what's that going to do? With less current, we're going to have less voltage drop across there, and that voltage is going to go up. So now what the regulator is going to do is shorten the duty cycle. Notice I have much shorter pulses here. And that's going to bring that voltage back down. So the regulator regulates not by, like I showed in the series regulator, where it's like holding a hand on the faucet and just adjusting it just right. As the demand goes up, you let more water out. As the demand goes down, you let less water out, and that keeps the voltage regulated. Here, it regulates the period of these pulses, the pulse width. Sometimes we call this pulse width modulation. So more demand, pulses get longer, or longer duty cycle, longer on time. Demand goes down, the pulses or the on part of the duty cycle goes less. And that's the basic idea of how a switching regulator works. Obviously more complicated than the series regulator we have done, but just to see if it would work, I tried to make one. I think if I were going to design one of these, I would do it a lot differently. In fact, you can take the LM723, and here is a circuit that they recommend to make a switching regulator. Obviously, if you can see the coil there, that acts as not only a filter, but also as part of an oscillator. It's going to use the op amps and some positive feedback to create an oscillator so that it has that on-off switching and then can regulate the duty cycle. And so it's kind of an oscillator and filter in one. But there are other circuits that are designed just to be switching regulators, and it's an integrated circuit. You design around it and makes it pretty easy, I would assume. I have not done it. But there's an oscillator that I give an example of in the operational amplifiers. And it looks something like this. We have our feedback here going to our inverting input. And we have some positive feedback here going to a capacitor. I'm not going to explain how this works right now because I have another video, I'll link in the description below, that does explain it. And here's our output. And this is going to go to ground. And of course, this goes to our minus voltage. And we have our plus voltage. And this will oscillate, and the oscillation frequency is going to depend on the time constant between this resistor and that capacitor, and it's going to depend on this voltage divider up here. So it's a little tricky, but like I say, I have a video that explains it in detail. But one interesting thing about this is I can put a circuit here and put a variable resistor there, and if I adjust this to be exactly the same as our ground, which would be 0 volts, I will have a symmetrical output. However, if I crank this upward, now off the top of my head I don't remember which way it's going to go, but if I go away from 0 volts here, so if this voltage here goes above 0, I'm going to shorten my duty cycle. It'll also change the frequency too, but that doesn't really matter. So the frequency is going to change, and just looking at it, I don't remember whether it's going to go up or down. We can look at that another time, but we just know if this goes up, the frequency changes, but the duty cycle also changes. And if I crank that down, it's going to change the frequency the opposite way and lengthen the duty cycle. So knowing that, I thought, could I make a power supply? And in this case, I just went straight to a load here without a pass transistor because it was just a proof of concept. And could I feed this voltage back to here such that if this voltage goes up, it changes this in the right direction to cause my duty cycle to shorten. And if this voltage goes down, it changes this such that my duty cycle gets longer and would therefore act as a regulator. Now, once again, it's been a long time since I made that. I don't remember whether going up or down changes it the right way, and I don't feel like trying to figure that out for the moment. But if this would not work, I simply had to put a little inverting circuit in here. So, quick inverting amplifier. I'll draw it properly here just because I can. Squiggly drawing, but it'll do. So I put a quick inverting amplifier in there, and it would just simply invert the voltage. So if this voltage goes up, that voltage goes down, and vice versa. So I did it one way or the other. I might have put a voltage follower here just to act as a buffer. So either a voltage follower or inverting amplifier, depending on which way it would work. And I tried it out, and as I changed this resistor here, which of course was going to ground, as I changed that resistor, it did change the duty cycle and did hold this. I would have had a big capacitor there, if I remember correctly, for a filter. And it did hold it at a fairly steady voltage, although of course I had ripple, but it did regulate. So it's very simple, just an oscillator that has a variable duty cycle, and I just fed back to it such that as this voltage goes up, the duty cycle would get shorter. As this voltage goes down, the duty cycle gets longer, and it did actually regulate. And if I wanted to, I could beef that up with a pass transistor and probably a good inductive filter and make a fairly good working switching regulator. But really, if I'm going to make one, I'm going to buy an integrated circuit and build one that way. So now that we have a switching regulator, we originally had that big hunking transformer in our original power supply, and that went to a, I'll just draw it as a diamond there, I want to be quick about this, went to a rectifier and a filter, and then to our regulator and pass transistor. And because this is dissipating a lot of heat, we have to have a big heat sink on it. And just to bring this down to a reasonable voltage, because if we didn't have this transformer, we would be starting with 110 volts. Instead of getting rid of 6 volts across here, we'd be getting rid of 114 volts. And so 1 amp of current and 114 volts, that's going to be 114 watts. So we have to have this transformer to step that down. So I have this big transformer, big heat sink, but with the switching regulator, which of course is a transistor, I'll just leave that there, but it just has a switching regulator, SR, getting a reference from something and turning that on and off. And since we're not producing anywhere near as much power here, we don't need to have that huge heat sink. And because we're not producing much power here, we don't need to step that voltage down. We can get rid of that big hunking transformer and go straight to our mains. So that's why a switching regulator is so popular. So if you pick up a power supply, whether it's a wall wart or anything else, and it's big and heavy, and you open it up and there's a huge transformer and a big heat sink for the pass transistor, you have a linear regulator. But if you pick up an equivalent power supply, whether it's a wall wart or bench power supply or whatever, and it's very light, and all you see inside is some rectifiers, capacitors, and a circuit and a big hunking, usually toroidal inductor, then you have a switching regulator. And now you can see why the switching regulator is so popular, because even though it's more complicated, it uses so little power and is much less expensive without the big transformer, which is expensive, and the big aluminum heat sink, and we can fit that on a smaller, lighter package. So switching power supplies are the way we go. So I hope you found that useful and informative, and if you did, please give me a thumbs up. It really helps the channel. And if you want to learn electronics technology, you can go to vocademy.net and take my free electronics course at Vocademy. And a big thank you to my patrons at Patreon who are making this all possible. To help me put these videos online and to help keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support, or look in the description below for a link to make one-time donations. Again, a big thank you to my patrons and a big thank you to everyone for watching.